My name is Alex Shang, and today let's first welcome the plenary talk from Chanwoo Kim from Samsung. Chanwoo is the Corp VP at Samsung Research, leading the speech processing lab. Chanwoo has led the end-to-end speech recognition and text-to-speech research and deployment at Samsung Research Lab. So if Chanwoo is ready, let's welcome Chanwoo to give the great talk.
Hi, everyone. This is Chanwoo Kim. Thank you very much for attending to my talk. As I introduced, my name is Chanwoo Kim, and I'm currently working for Samsung Research in Seoul, South Korea. Today, I talk about the on-device end-to-end speech recognition systems. So in this slide, you can see the contents of today's talk. So at first, I talk about the requirements for on-device speech recognition. And before talking about the end-to-end neural network-based approach, I will briefly talk about the conventional WFST-based speech recognition systems. So WFST stands for Weighted Finite-State Transducer. And in the next section, I'll talk about the main topic of today's talk. So I'll talk about the end-to-end fully neural end-to-end speech recognition systems. And we will cover 3 different architectures: the encoder-decoder approach, and attention-based encoder-decoder approach, and also RNN-T based approach. And for on-device speech recognition, actually one of the most important factors might be the model compression. So I'll talk about what kinds of techniques have been employed for successful on-device speech recognition. And finally, I'll talk about how we can further improve the performance, and I will end up my talk with a short conclusion. So as Samsung Research, actually we have commercialized several on-device end-to-end speech recognition systems already. So we commercialized our ASR engine for air conditioners and the flagship mobile phones and so on. So for on-device speech recognition, actually the requirement is a little bit different from server-side speech recognition. So one of the most important things might be the size. So we need to care about both the parameter size and also the memory footprint. So, and also we need to care about the computational cost and also the latency. So for commercial speech recognition systems, we usually want to keep the latency less than 200 milliseconds, which means that if the user finishes speaking his or her utterance, then we usually expect that the recognized sentence will appear within 200 milliseconds. And for on-device speech recognition systems, usually for mobile phones, it's powered by a battery. So we also need to care about the power consumption issue as well. And for on-device speech recognition system, actually we have limited memory and memory and storage space. And for personalized words like named entities or personal phone book, actually we should be able to handle those kind of personalized named entity information. So we will talk about how we can tackle these issues. So before talking about the end-to-end speech recognition systems, I first briefly talk about the conventional techniques. So neural network end-to-end speech recognition system appeared roughly in 2015 or in 2016. So there was seminal papers about end-to-end sequence-to-sequence modeling on machine learning first, and after that, people started using those attention-based encoder-decoder approach to speech recognition as well. And before that time, actually, people have been using hidden mark model-based approach. And in the conventional techniques, actually, it consists of many different parts. So because this is not the main topic of today's talk, I'll just briefly talk about what components existed in the conventional techniques. So in conventional speech recognition systems which existed before like 2017 or 2018, it consists of acoustic modeling part, which is often abbreviated as AM, and the language model part and the pronunciation model part. For language model, actually, we usually use the n-gram model, which is a statistical language model, and for AM we use the hidden Markov model and the Gaussian mixture model. And for pronunciation model, we have been using dictionaries. So dictionaries are usually handcrafted. So to make the dictionary, actually it requires a lot of efforts. It requires a lot of human efforts. And for decoding, we usually use the weighted finite-state transducer. Especially to obtain high performance, actually the language model is actually very large. So the entire size of WFST can be extremely large if we want to achieve a high speech recognition accuracy. For example, for the server-side speech recognition system, which was deployed at Google system, I remember that the size was like 80 gigabytes or so, because it includes a lot of words in the dictionary, right? 4 million words or even more in the pronunciation dictionary, and the language model is enormously large. So it's not easy to commercialize those kind of high performance systems for on-device applications. But as mentioned before, the end-to-end neural speech recognition systems appeared roughly for commercial purpose. Actually, I believe that the first commercialization might be from Google, roughly in 2019, as far as I remember. And as Samsung Research, actually, we commercialized the end-to-end speech recognition systems for mobile phones in November 2019. So in the conventional system, as mentioned in the previous slide, there are many different components, and all these components were constructed using different technology, such as hidden Markov model, statistical n-gram, and some kinds of dictionary, and so on. And in the end-to-end speech recognition system, actually everything is trained as a big chunk of a neural network. So the structure can be much simpler, and it's much more compact. So this end-to-end speech recognition system is much more appropriate for on-device applications compared to conventional ASR systems. So in this page, actually, we show a little bit on different end-to-end speech recognition systems. So the first end-to-end speech recognition systems may be CTC-based approach, and in CTC stands for Connectionist Temporal Classification, and it's actually a kind of sequence loss. So in the neural network, actually, the most widely used loss function might be the cross-entropy loss. But for speech recognition systems, actually, we need to handle sequence information. So Alex Graves, who is currently working at Google, published a paper at ICML 2006 about CTC loss, and this CTC-based approach might be one of the first end-to-end speech recognition systems. But in the CTC-based approach, actually, you can see that there are no feedback paths from the output to the input. So actually, the performance for long sentences might be a little bit poor because it doesn't have any kind of feedback. And in the CTC loss, actually, one of the assumptions is like conditional independence assumption. So to satisfy this assumption, actually, it's not easy to add a kind of output feedback path. So to improve the performance, the same author introduced the RNN-T based structure. So this paper appeared in 2012 and 2013. So he first published in ICML workshop in 2012, and in his, I guess, 2013 paper, the structure was discussed once again. The RNN-T based approach is somewhat similar to the CTC based approach, but it has three different components. The first part is the encoder part, which is colored in light green. And in this case, actually, we are using a stack of LSTM layers. But instead of LSTM layers, actually, we can use other structures like convolutional neural network or transformer encoder and so on. And the other part is the prediction network. So in the prediction network, I use the orange color. So prediction network is doing some similar role to a language model. So prediction network is actually predicting the next symbol. And this encoder part and the prediction network parts are connected to the joint network. So all three components are trained all together. So this is the RNN-T based approach. And still, the other end-to-end sequence-to-sequence approach might be the attention-based approach. So I think that you might be quite familiar with the attention-based approach because this technique is really popular in machine translation and like natural language understanding and so on. So it's a very important technique. So this technique was first introduced roughly in 2015. And it was first employed for machine translation. And later on, people started using this technique for speech recognition. So Jankowski published a paper in NIST 2015, and William Chan also applied attention-based model for speech recognition. Actually, he did work in 2015. So at that time, I was also working for Google speech team. So he did an internship at Google at that time, and he published the paper in, I guess, 2016. So those are the first attention-based approach in speech recognition. And those attention-based approaches were commercialized for commercial products roughly in 2019. So I'll briefly talk about the CTC algorithm a little bit. So speech recognition is a little bit different from image classification because the input is text, the output is the text, and the input is the acoustic waveform. And one problem is that usually when you train the speech recognition model, for example, in this case, actually, we don't know the exact location of the character Y in the waveform. So we don't have any kinds of phonetic alignment information from the label. So that's one difficulty in directly applying the cross entropy loss when we train the sequence-to-sequence speech recognition model. So Alex Graves proposed the CTC loss. So in CTC loss, actually, it's still a CE loss. So it's still based on the cross entropy loss, but because there are all different possible alignments. So actually, he did a summation to cover all possible alignments. So in this equation, the symbol Y represents the text, and the X represents the input acoustic feature. So by using the conditional independence assumption, actually he represented the sequence probability as a product, and he actually summed up all possible alignments. So the idea of the CTC loss itself is quite simple. So he just considers all possible alignments which can map the input waveform to the actual text sequence. And like any other loss function used in machine learning, we use the log probability with the expectation. So this is the definition of the CTC loss, and this work was published by Alex Graves in ICML 2006. So as I mentioned before, actually in the CTC loss, actually he based on the conditional independence assumption. So his CTC loss block can be used for layers of GetSTMs or for layers of CNN layers. But for language modeling, we know that we need a kind of feedback pass. So feedback pass means that once we have the output, then we want to predict the next symbol based on the current output. But if we use the CTC loss, then it actually heavily depends on the very strong conditional independence assumption. So we cannot explicitly add the feedback pass. So he actually modified his previous work a little bit, and he added the prediction network. And the role is somewhat similar to a language model block, which can predict the next label. So he combined this prediction network and the stack of either LSTM or CNN layers, and he connected those two components to a joint network. So this is the RNN-T structure. So RNN-T stands for Recurrent Neural Network Transducer. But recently, actually, people have been using this structure to various kinds of encoders, like CNN or like transformer or like conformer. Conformer stands for convolution augmented transformer. So actually, we can use various kind of structures for the encoder part. So in our case, actually, we commercialized our on-device DSR system using the attention model first, and in this year, actually, we commercialized the on-device ASR system based on RNN-T. And another famous sequence-to-sequence approach might be the attention-based approach. And in the attention-based approach, we have the input sequence and the output sequence. And in 2014 paper by several researchers, actually, we can use the LSTM to convert variable length input to a fixed vector, fixed length vector output, and we can use the decoder to generate the sequence. So that's the basic sequence-to-sequence approach using the encoder-decoder. And later on, it turns out that if we use the attention model, then we have the capability of focusing on a certain point of the input. So by using the attention mechanism, actually the performance, especially motion translation, improved a lot. So the same technique was also employed for speech recognition as well. So in the attention-based approach, we have the LSTM layers, which is the encoder, and we have the attention block, and we have the decoder block. And for training the attention-based model, unlike the previous RNN-T or CTC-based approach, we usually use the cross-entropy loss. And almost always, actually, we are using teacher forcing approach. So in the teacher forcing approach, during the training phase, instead of using the inference output, we use the ground truth label to train the decoder portion. So we this attention-based approach is quite popular. However, the problem of the attention-based approach is that if we use the attention-based approach, it requires that the entire input feature should be encoded first before generating the first output label. So actually, it will significantly increase the latency. So it means that until the user finishes his or her speech, actually the speech recognition system will not generate the first output character. So it has a serious problem for streaming speech recognition. So to tackle this problem, actually people develop some kind of streaming attention. So one example might be the MoChA attention. MoChA stands for Monotonic Chunk-wise Attention. So it's a kind of streaming attention, and I will talk about this algorithm in better detail. But in MoChA attention, actually, it consists of two attention layers. The first one is monotonic attention, and the second one is chunk-wise soft attention. The first monotonic attention is like a hard attention, which is represented by like one spot. And the second attention is more similar to the conventional attention, which is a soft attention. So in this figure, we can compare the conventional soft attention and the hard monotonic attention and the MoChA approach. So MoChA is the monotonic chunk-wise attention, which is shown in figure C. So in the soft attention, actually, so in this figure, the x-axis represents the input time index, and the y-axis represents the output label index. So in motion translation, when we translate one sentence in one language to another sentence in another language, actually we know that like word sequence in different languages might be also different. So in motion translation applications, actually there's no guarantee that the attention, the attending point will increase monotonically. But for speech recognition, we know that as we speak, actually the output label always proceeds. So that's actually the motivation of the monotonic attention. So in hard monotonic attention, as mentioned before, we only care about one single attending spot, and we assume that this attending spot should increase with respect to time. So as the user speak, the attending point increases. So that's the hard monotonic attention approach. But the problem is that the performance of this approach is worse than original soft attention. So to obtain better performance, people combine the soft attention approach with this hard monotonic attention approach. So after finding the attending point, they constructed a window, which is also called a chunk. And within that chunk, they use the soft attention with the soft values. So the equation itself is almost the same as the conventional attention approach. So, and this approach is the monotonic chunk-wise attention, which is often called MoChA, and it shows comparable performance compared to the original soft attention. And now let's talk about the model compression. So by using this neural network-based approach, actually the model size is much smaller than conventional WFST-based approach. So for example, to obtain a relatively good performance for open domains, then we can usually use for example, 100, 1 mega parameters, but 100 mega parameters, but still it's too large for air conditioners and so on. So there have been many different techniques to reduce the model size. So in speech recognition, actually, we have tried many different techniques. One example might be the knowledge distillation approach. And this technique is quite effective. And we observed that in our recent commercialization, knowledge distillation techniques seems to be better than other techniques for ARM processors. And one popular technique is the quantization. And if we use the TensorFlow right, then I think that many people are currently using 8-bit quantization. So 8-bit quantization has been almost always adopted for commercial ASR products. And we also use the 8-bit quantization. And if we are a little bit more ambitious, then we can try 1-bit or 2-bit quantization, but usually it's not very easy to maintain the performance. And also the other issue is that if we use 1-bit or 2-bit quantization, then with the application processors, usually we don't have 1-bit or 2-bit arithmetic units. So people usually use 8-bit quantizations, but sometimes we use 4-bit quantization or less. And low-rank approximation is also popular. So neural networks can be represented as a matrix multiplication, and by using the SVD, singular value decomposition, and the low-rank approximation, actually we can reduce the size of matrices. So by reducing the size of matrices, actually we can reduce the model size. And the other technique might be the pruning technique. So by using the pruning technique, actually, we can remove some small parameters in our model. So if we have a good software toolkit or a hardware infrastructure which can handle sparse matrices, then pruning technique might be quite useful. But if we don't have a good hardware which can handle sparse metrics, then probably pruning technique might be less effective compared to other techniques. And in this slide, actually, we can see how we compressed our model using the LRA. And in this table, actually, we can see performance. So in our case, actually, the original model size was 530 megabytes for Korean speech recognition systems, but eventually, we could reduce the model size to 35 megabytes by using SVD technique and 8-bit quantization while maintaining the speech recognition accuracy. So the final model size is less than 1/10 of the original model size. And for customized speech recognition systems, for mobile phones or and so on, actually people usually store his friend's name and his friend's phone numbers, and the speech recognition system should be able to recognize those personalized numbers and those personalized names. To tackle this problem, there have been several technologies. One easy way might be constructing a custom language model and applying a shallow fusion with an external RM. So this approach is actually very simple. So as you can see in this equation, shallow fusion approach is just doing a linear interpolation of the log probability obtained from the speech recognition model and the log probability predicted by the language model. So by constructing a language model using the custom information, we can build a custom speech recognition system. So shallow fusion itself is very simple. So we just combine an external RM with the end-to-end speech recognition system. So as you can see in this table, so you can see a table in the bottom of this page, then we can see that for specialized domains like context, so context means like personal names, his friend's name are stored in the phone book, then we can see that after doing some kinds of adaptation, actually the performance actually increased a lot. So in speech recognition system, we usually measure the performance in terms of word error rate. So it means what's the percentage of incorrect words. So if the word error rate is 15%, it means that 15 words out of 100 words are incorrectly recognized. So after doing some adaptation, then we can see that word error rate was reduced to 11% from original 15%. For general domains, actually, there's almost no improvements, but for specialized domain like IoT. So in IoT, then we should be able to recognize the device name and device functionality. So in those specialized domains, by using this custom RM, actually, we can significantly improve the performance, improve the speech recognition performance. And in this page, actually, we compared the two famous techniques. So previously, we talked about the RNN-T based approach and also the MoChA based approach. So MoChA is the streaming attention, and RNN-T is like a structure including encoder and the prediction network and joint network. So we compared the speech recognition accuracy and model size and latency. In terms of speech recognition accuracy, we observed that MoChA might be a little bit better, but in terms of latency, we can see that RNN-T is much better. So because of this reason, actually, these days, actually, we are switching from MoChA-based streaming attention to RNN-T or conformal-based speech recognition. So it's also called conformal transducer. So the structure of RNN-T and conformal are very similar. So in terms of latency, it seems like RNN-T based approach seems to be better. So far, we observed that for general domains, actually the on-device speech recognition system is actually on par with the server-side speech recognition system. So actually, that's quite amazing. So previously, we required like 80 gigabyte or 100 gigabyte to achieve the state-of-the-art performance. But just using like 100 megabyte on-device speech recognition system, the performance is almost similar to the server-side performance. But we observed that for specialized domains like named entity recognition, still on-device speech recognition system is not as good as the server-side speech recognition systems. The primary reason is that on the server-side conventional engine, it requires like very large dictionary. So in the dictionary, actually, it includes a lot of named entities like trademarks, personal names, and geographic names. So all those named entities are handcrafted and included in the dictionary. But for on-device speech recognition systems, actually, we don't have such kind of components. So for general open domains like dictation, our on-device speech recognition system is on par with the conventional WFST-based approach, but for named entity recognition, the performance is somewhat behind. So to handle this problem, actually, we try to improve our on-device speech recognition system. So in this slide, actually, we show a hybrid like causal and non-causal combination approach. And in our commercialized ASR system, we employed this technique. So we know that bidirectional LSTM will show better performance than unidirectional LSTM. But if we use the bidirectional LSTM, which also has the backward pass, then it requires that we need to have the entire feature sequence before doing the before generating the first output label. So bidirectional LSTM is much better in terms of performance, but it has some problems in terms of latency and the computational cost. So in our implementation, actually, only at the top layer, we added the backward LSTM. So basically, only the top layer is the bidirectional LSTM. So we have two different decoders. One is the streaming MoChA attention. So using the streaming unidirectional LSTM and the streaming attention while we are speaking, then we can generate the streaming speech recognition result using this part. And once the user stops his or her speech, then we can use the bidirectional LSTM and the full attention. Since actually we already calculated all these values, actually we don't need to recalculate the encoder values. So we already have those values, and once he stops his or her speech, then we only do the like full attention. So it doesn't impact the latency that much while improving the speech recognition performance. So in this table, we can compare the unidirectional encoder and the streaming attention-based approach. And in the standard library speech test, we can see that the word error rate is roughly 6.88%. But if it is the bidirectional attention approach with the full attention, word error rate is much better, much better. It's 3.62%, but we cannot commercialize those kind of systems because it doesn't meet the latency requirement. But by using this causal, non-causal hybrid approach, actually Google published a paper about this, but actually we published the paper a little bit earlier than the Google approach. So we can see that the performance is very similar to the bidirectional approach case, while still satisfying the latency requirement. And I will skip this slide. In this slide, actually, we are showing that we are doing extensive data augmentation, and the data augmentation is running on the CPU cluster for the training phase, and parameter updates are on the GPU cluster. And in this slide, we can see the named entity correction. So previously I mentioned that the neural network-based approach is quite good for open domain, but I mentioned that the performance might be somewhat behind for recognizing named entity. So for on-device recognition, once we know the domain, so domain means the speech recognition domain. For example, music domain or the core domain. So we apply a kind of domain classifier to find out what's the current domain that usually is speaking, and based on the domain, then we usually list of words. So we use a kind of limited word sequence, named entity sequence. So based on the named entity sequence, actually we applied kind of hierarchical named entity matching. So as you can see, we first do like word level matching, and after that we use the double metaphone approach to do some kinds of phonetic level match. And after doing that, finally we use the grapheme level match. So grapheme means the character. So instead of using this kind of approach, actually we can first start with the grapheme level approach. But in that case, then because in the named entity list, because there are so many words, it requires a lot of search space. So computational cost might be too large. So by using this kind of a hierarchical approach, actually, we can reduce the computational cost while achieving good performance. So as you can see in this table, for those specialized domains like music domain, which includes a lot of song names, by using this named entity correction mechanism, we can significantly improve the performance. This is the final page of my talk. So today, actually, we briefly talked about the contemporary on-device speech recognition systems using neural network technologies. So the performance of the on-device ASR systems have improved significantly after the introduction of fully neural end-to-end DSRs, and there are a few different structures like attention-based approach and streaming MoChA attention, and also RNN-T based approach. And people have been doing model compression using various technologies like quantization, row rank approximation, and also pruning, knowledge distillation, and so on. So fortunately, thanks to those techniques, actually now we could commercialize on-device fully neural end-to-end speech recognition systems for mobile phones and air conditioners and the refrigerators and so on. And the benefits are actually obvious. So we can enhance the privacy and reduce the server cost, and also can reduce the latency. So there are a lot of benefits, and still, but there are still remaining challenges. The remaining challenges might be still reducing the computational cost, and also the named entity recognition performance should be still improved. So there are still remaining challenges. So this is the end of my talk, and thank you very much for your attention. Thank you.
Thank you, Chanwoo. Any questions from the audience? This is a good opportunity to have interactive discussions with the speaker. While the audience may think about their questions, may I ask Chanwoo regarding, thanks for the deep research and the introduction of the analysis of the end-to-end speak recognition. A question from my side would be any recommendation or thoughts on the hardware underlying to process the models, the solution, and also any advantage could bring from the specialized neural network processor could give value, could help.
Yeah, thank you very much for your question. So I think that this is a very good question, and this is a very important question. So far, actually, instead of using NPUs, so far actually we have been using ARM processors for speech recognition systems. I think that the reason is that until recently, actually, we have been using LSTM-based approaches. And in case of the LSTM-based approach, actually, it's not very good for parallelization because there is the recurrent structure. But in future, I think that we will more focus on transformer-based approach and also conformer-based approach. And in that case, actually, parallelization might be much easier. So we believe that NPU might be very, very important in the future. So So far, actually, we have been usually using the ARM processors for air conditioners and mobile phones, but we have been actively working with hardware team to use the NPUs. So if we use the NPUs, then we can significantly reduce the power consumption. That's actually the biggest advantage. And for on-device speech recognition, actually, like for some applications like mobile phones, the battery life is really important, and in the future, I think that people will use speech recognition for like video conferencing or like Zoom communication, and in that case, actually, the speech recognition system might be running for like 30 minutes and for hours. So in terms of power consumption, actually, I think the NPU might be much more efficient. So in future, I think that NPU might be really important.
Great. Yeah, thank you. Fully agree. Another question from audience is that can the end-to-end ASR be applied on low? I mean, it's kind of a related question, right? So, but if you can answer that directly, applied on low-end edge devices, which has different constraints of the hardware, with model size like less than 10 megabyte.
So low-end edge device, like less than 10 megabytes. So I think that that's also like a very interesting question. So far, actually, we commercialized our ASR systems for mobile phones, and for mobile phones, actually 30 or 40 megabytes might be fine. But for some like low-end devices, like for example, like low-cost air conditioner, or like some wearable devices like watch or earbud, actually the requirement is very tough. So we have been using special libraries, and also and in the case actually so I think one person mentioned like TensorFlow Lite. So TensorFlow Lite is actually like a very popular technique, but in some cases we even like using custom optimization to even reduce the model size. So far, actually, we tried model compression technique to reduce the model size less than 10 megabytes, but in some cases, we found that it's very challenging to compress the model size. So in today's talk, actually, I briefly mentioned the CTC-based approach, and actually CTC-based approach like smaller memory footprint. So for wearable devices, actually, we are also considering like a CTC-based approach, and those might be like very useful. So I think that probably NPU might have, and also we like different neural network architecture as well. So for those like low-end edge devices, then probably instead of obtaining a performance similar to server-side speech recognition system, actually the target should be command recognition. So for command recognition, I think that still we can obtain a reasonably good performance using a model with less than 10 megabyte memory footprint. Thank you.
Great. Thank you. Thank you again, Chanwoo, for your. Oh, okay. Let's another question coming in. Okay, so okay, actually we have two questions, but maybe you can address quickly. One is there another approach for quantization without using TensorFlow Lite? The second one is speech recognition and closing captioning is being incorporated more lately to increase accessibility, AI for good. Do you see MoChA being incorporated into more hardware in the future?
Okay, so I will answer those questions. So for quantization, actually, for commercial purpose, actually, we have been using TensorFlow Lite, but we also explored into 4-bit or 5-bit quantization for like keyword spotting application. So I think that approach is also very good. So we can actually do like forward 5-bit quantization, and in our lab, actually, one researcher actually did some research in this aspect. Actually, but the problem is that because so far we have been using usually ARM processors, actually it doesn't have any 4-bit or 5-bit ALU. So the like improvement is actually somewhat limited. But in the future, I think that if we have a dedicated NPU, I think that in the future, I believe that there will be a lot of NPUs which might be suitable for typical records. And then I think that custom quantization will become much more popular. So for quantization, it has a lot of potential, but because of the limitation of the hardware, actually people have been usually using TensorFlow-like AP quantization. And for the second question, actually, I couldn't clearly understand the question. So I think that So what was the second question? So
okay,
let
me repeat that.
Okay.
Yeah, let me repeat that question to you. So basically, the speech recognition and the closed captioning is being incorporated more lately to increase accessibility, AI for good. So do you see MoChA being incorporated into more hardware in the future?
I see. So like the video captioning technique. So these days actually we are almost giving up the MoChA approach. So I think that probably MoChA means MoChA. So MoChA is the streaming of attention-based approach. So in future, I think that for like video captioning or like video conferencing, those like streaming speech recognition might be very, very important. But I think that instead of using MoChA, we can probably still use the conformal transducer or RNN-T. And probably those systems are better in terms of latency and also in terms of performance. Also, actually, in today's talk, I mentioned that MoChA is a little bit better in terms of accuracy, but we observed that for long sentences, actually, RNN-T based approaches seems to be better. So probably I think that for video captioning, RNN-T or conformal transducer might be better approach than MoChA based approach. And I think that in the future there will be a lot of applications like video captioning and like video conferencing and so on. Yeah. Thank you.
Great. Thank you. Thank you for the good questions and the interactive discussions. So thanks again.
We want to thank especially our strategic partners who have made it possible. We have our executive sponsors, ARM, the Software and Hardware Foundation for tinyML, then at Impulse tinyML for all developers, Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous, Sentient end-to-end deep learning solutions for tinyML and Edge AI, then Platinum sponsors, Reality AI, add advanced sensing to your product with Edge AI, tinyML, and then Renaissance, broad and scalable edge computing portfolio. Our gold sponsors, Latent AI, adaptive AI for the intelligent edge, Maxim Integrated, enabling edge intelligence, Seed Studio, the IoT hardware enabler, SensiML, build smart IoT sensor devices from data, SynSense, build sensing and inference hardware for ultra-low power embedded mobile and edge devices. And our silver sponsors, Aeon Devices, Deep Light, EMSA Visual Sense, Greenwaves Technologies, Gravity Inc., HODG, Imagimob, Kixo, Rixen Technology, and SAP. So thank you everyone for staying with us today, and see you tomorrow.